The number and arrangement of protons and electrons in different elements follow a predictable pattern, allowing us to organize the elements in a meaningful way. The most popular of these is the periodic table. Each element has a cell in the table containing the following information: the element's name in small letters, a large 1 or 2 letter symbol for the element, and each element has its own unique symbol. Above the symbol is the atomic number. Each element has a different atomic number, which is the number of protons in its nucleus. This number defines the element. At the bottom is the average atomic mass of the element. Generally, this is the number of protons and neutrons in the element, but it is never a whole number. So what does average atomic mass mean, and why is it not a whole number? The reason is that the average atomic mass is the average mass of all the atoms of that element, and elements have different forms. These different forms are called isotopes. Take an atom containing 1 proton and no neutrons in its nucleus. We know this atom has an atomic number equal to the number of protons in the nucleus, which in this case is 1. Looking for the element with the atomic number of 1 in the periodic table would tell us this is hydrogen. It is hydrogen due to the number of protons in the nucleus. If it had some other number of protons in the nucleus, it would be some other element. However, if it had some other number of neutrons in its nucleus, its atomic weight would change, but it would remain a hydrogen atom. And while most hydrogens have 1 proton and 0 neutrons in their nucleus, there are other forms of hydrogen. To distinguish between them, we use isotope notation. This notation shows the element symbol with a subscript to the left of the symbol showing the atomic number and a superscript to the left showing the mass number. Notice we are using the term mass number here and not average atomic mass because we are now describing the characteristics of a specific form of the element. The most common form of hydrogen is written in isotope notation this way: superscript 1, subscript 1, H. There are other isotopes of hydrogen. Some atoms contain 1 proton and 1 neutron. The single proton means they are still hydrogen, but the additional neutron gives them a mass number of 2. There are also atoms with 1 proton and 2 neutrons, still 1 proton, so still hydrogen, but 1 proton plus 2 neutrons gives them atomic mass number of 3. To distinguish between different isotopes of an element, we call them by their element name followed by their mass number. So these 3 isotopes of hydrogen are hydrogen 1, hydrogen 2, and hydrogen 3. In the case of hydrogen, the heavier isotopes have their own names. Hydrogen 2 is called deuterium, and hydrogen 3 is called tritium. This is unusual. Most isotopes are distinguished by their mass number. The average atomic mass number is an average mass based on the abundance of the different naturally occurring isotopes of hydrogen. It is very, very close to 1, meaning most hydrogen is hydrogen 1, but small amounts of naturally occurring deuterium and even smaller amounts of naturally occurring tritium make the average mass of hydrogen slightly greater than 1. A quick look at the periodic table reveals that all of the naturally occurring elements have multiple isotopes. None of them have whole number average atomic masses. In introducing the atom, the neutron was described as playing a role in stabilizing the nucleus. While this is true, it doesn't mean that any proton-neutron arrangement is possible or that more neutrons are always a good thing. Not all possible nuclear arrangements are stable. Most arrangements are so unfavorable that they cannot exist, or if they are formed in some way, they only last a fraction of a second before breaking down. Others are perfectly stable and will last forever. Between these two are nuclear arrangements that are unstable enough that they will break down, but stable enough to last for some period of time. These are the common radioactive isotopes. When radioactive isotopes break down, they are converted into energy and other isotopes. Sometimes these isotopes are different forms of the same element, and sometimes the breakdown causes the addition or reduction of the number of protons in the nucleus, resulting in the atom becoming a completely different element. This breakdown is called radioactive decay. The degree to which a particular isotope is stable is described by its half-life, which is the amount of time required for half of the isotope to be broken down into other isotopes. The longer the half-life, the more stable the isotope. The decay of radioactive isotopes is not a linear process. If we start with 100 atoms of a particular radioactive isotope, after one half-life, only half the atoms would still be present. The other half will have decayed into some other isotope of either the same element or a different element. After an additional half-life, half the isotopes present after the first half-life have decayed. This pattern continues with only half as much of the original isotope present after each half-life. It takes many more than 2 half-lives for most of the radioactive isotopes to decay into other isotopes. Many elements, including hydrogen, have both stable and unstable isotopes. For hydrogen, both hydrogen-1 and deuterium are stable, while tritium, with 1 proton and 2 neutrons in its nucleus, is radioactive with a half-life of 12 years. Radioactive decay occurs in fixed patterns with specific radioactive isotopes decaying into other specific isotopes. For example, tritium with its half-life of 12 years, a mass number of 3, and 1 proton in its nucleus, decays into stable helium isotopes having the same mass number of 3 but 2 protons. The decay of radioactive isotopes is associated with the release of energy. This is what we call radioactivity. We can look at other entries on the periodic table to learn about some common elements. Carbon has 6 protons, and the most common form has 6 neutrons, giving it an average atomic mass of about 12. Nitrogen has 7 protons, and the most common form has 7 neutrons, giving it an average atomic mass of about 14. Oxygen has 8 protons, and the most common form has 8 neutrons, giving it an atomic mass of about 16. The most common isotope of carbon is carbon-12. Carbon-13 is also stable. A common radioactive isotope of carbon is C14 with a half-life of 5,730 years. Nitrogen-14 is one of the 2 stable isotopes of nitrogen, the other one being nitrogen-15. The most stable of the radioactive isotopes of nitrogen is N13 with a half-life of only about 10 minutes. In addition to oxygen-16, measurable amounts of oxygen-17 and oxygen-18 are present on Earth. None of the radioactive isotopes of oxygen have half-lives greater than a few minutes. Like these 3 elements, all naturally occurring elements have multiple isotopes. Some are stable and some are radioactive.